Hello and welcome to the 6th week of the course Collaborative Robots Theory and Practice. This week I will cover robot dynamics through following lectures. So I will start introducing you all to robot dynamics. I will discuss what is Lagrange-Euler approach. We will do 1 degree of freedom system dynamics using Lagrange-Euler approach. In the second lecture I will continue using Lagrange-Euler approach to derive equation of motion for a two-link manipulator. In the third lecture, I will introduce you to Newton-Euler approach and recursive Newton-Euler approach. In the fourth lecture, I will use Newton-Euler approach to deduce equation of motion of a two-link manipulator. So, welcome to the first lecture now, that is on robot dynamics. So, overview of this lecture would be as follows. In this lecture, I will introduce you to robot dynamics. I will discuss Lagrange-Euler approach. I will do spring mass system using Lagrange-Euler approach, and I will do one link pendulum or an arm using Lagrange-Euler approach. So, let us begin with robot dynamics. Why do we need dynamics? That is to do analysis of links of a robot due to its own weight, due to external forces or moments. So, this is also to study torques and forces that causes motion in the robot. You can develop equation of motion that describes the dynamic behavior of the robot, which can later be used for developing controller for the robot in real or in simulation. Okay. This is also used to design links, bearings, transmission systems and for actuator selection. Okay. So, what is forward dynamics or a direct dynamics, commonly known as forward dynamics? So, forward dynamics are required to find out response of a robot arm corresponding to applied torques or forces at its joints. So, let us say you have a robot which looks like this, a two-link robot, let us say. So, if you apply joint 1 with torque 1 and joint 2 with torque 2. So, you want to study the effect of those torques at the end effector or the link velocities or any joint motion you want to get. So, all these can be obtained using forward dynamics. So, forward dynamics is essentially the study of robot motion corresponding to the joint forces or torque. In case of rotary joints it is torque, but in case of prismatic joint they are forces. So, it is primarily used for computer simulation, which shows how a robot or a cobot will follow the trajectory under given forces and torques. Okay. And what is inverse dynamics? It is a way out to find out actuator torque and or forces does it required to generate the desired trajectory of the robot's end effector. So, if you have already the trajectory in your hand, you already, let us say you want to apply a robot for, let us say, painting operation. You already know what should be the motion of the joint, what should be the end effector motion. So, everything is known. So, now you want to know what should be the profile of the trajectory of your joint torques or the forces which actually creates that particular motion. So, this kind of job is done using inverse dynamics. So, an efficient inverse dynamics model becomes extremely important for real time model based control of the robot. If you want to create your own controller, that we will see later in the robot controls week. Okay. So, we will be using this to create such controller models. Okay. It helps in selection of actuator. If you know the torque profile for a given motion which is possible by your robot, so you can select the actuator which can actually generate those kind of torques. So, it helps you in selection of those actuators and other parameters related to the robot. So, maybe you want to design the robot link and you have already tested the joint torques, those torques and forces will become actually the boundary condition for the link design. Considering the dynamic forces also, you can design your robot. So, these are the places where forward dynamics will be helpful. Okay, so let us begin with Lagrange-Euler approach here. So Lagrange-Euler formulation is defined as this. So the Lagrange-Euler formulation requires knowledge of kinetic and potential energy of the physical system. You need to know the masses of the link, you need to know the moment of inertia of the link and mass center of the link. So all these parameters should be well in hand before you begin calculating the joint torque or the forces using Lagrange-Euler formulation. This formulation is given by d by dt of dou L by dou q dot minus dou L by dou q is equal to phi, where I is equal to 1, 2, 3, 4 at right up till n. N is the degree of freedom of this robot. Okay, so what is L? L is kinetic energy K minus P, that is potential energy of the system. Here it is system. Okay, and Q is the angular or linear displacement, and phi is the generalized force in case of prismatic joint, and torque tau in case of revolute joints, okay, for the ith joint. So if you do this, L is for the whole system, but when we do partial derivatives, we do with respect to a particular joint. So those joint torque or forces will be obtained using each individual equation. Okay, so let us start using it here for a simple spring mass system using Lagrange-Euler approach. So this is a 1 degree of freedom system. When this mass can move along a straight line, it is sliding on this fixed surface, smooth surface, frictionless surface. Okay, this is the spring which is attached to the wall which is here, and other end is attached to the mass. Okay, and spring has the stiffness of K. Okay, this is frictionless surface. So only forces that are affecting this is maybe any external force or the spring force. That's all. At equilibrium, it remains here. Okay, it can be displaced from this along any of these two directions. So along x, let us say. So for any given displacement x from the mean position, that is this, kinetic energy will be equal to K is equal to 1 by 2 m x dot square. What is x dot? X dot is rate of change of x, that is velocity square. Okay. Similarly, potential energy will be only due to the spring which is there. It is not moving against or towards the gravity, right? So it is not along the gravitational forces. It is, if G is like this, it is moving perpendicular to that. So only forces are because of this spring. So this causes potential energy to be stored in the spring, and how much is that? It is 1 by 2 kx square. X is the displacement from the mean position, K is the stiffness of this spring. Okay. So Lagrangian now will be equal to kinetic energy minus potential energy for the whole system. Okay. So it is equal to 1 by 2 m x dot square minus 1 by 2 kx square. So for LE expression, Lagrange-Euler expression, this should give me now the force that is actually causing this motion. So it is defined by this. In this case, your joint displacement is this, that is the displacement, linear displacement, and what you obtain is the force because it is a linear displacement. Okay. So I will go by the first bracketed term which is here. I will use this Lagrangian, take derivative with respect to xi dot. I is 1 here, so it is only one displacement. Okay. So dou L by dou xi dot is equal to dou by dou x dot of Lagrangian that we have obtained here, and that gives me this. So you see, second term does not have x dot term, so effectively that would go to 0, and only term which remains is this. Okay, that finally gives me m x dot. So dou L by dou x dot is equal to m x dot. If I take time derivative of that, so I get m x double dot. Okay. So this is the first term of LE expression. The second term would go like this: dou L by dou x would only consider the second term of this. Okay. Why? Because this has x, this does not have x. Okay. So, that is treated as constant, and dou L by dou x will give you minus of 1 by 2 k. So, dou by dou x of x square is 2x. So, effectively taking derivative gives me minus of kx. So, now I have both the terms of my LE expression. So, using LE expression now gives me this. So, mx double dot plus kx is equal to F. F is the force. The above expression is the dynamic equation of motion of a spring mass system. Using Newtonian mechanics also, you know already, summation of all the forces is equal to mass into acceleration. So, we can use it here as well. So, synthesis using free body diagram, we can get the same expression. So, your free body diagram for the block would go like this. So, F minus kx is actually producing the acceleration. So, it is mx double dot or ma. So, both are same. So, you can directly write this. Okay. So, if I rearrange it, I can again obtain the same expression as this one. So, F is equal to mx double dot plus kx. So, you see you can obtain free body, you can use, so you see you can use Newtonian mechanics or using free body diagram also to obtain the similar kind of expression as you can deduce it using LE equation. What is the benefit of using LE equation now? So, you see in this case you need to draw the free body diagram of all the connected bodies. Okay. But in case of LE equation, that is the energy based method, it does not do that. You do not have to calculate the forces which are in between two connecting bodies if it is there. You can directly use the displacements and the velocities to calculate the energy and take derivative, get the equation of motion. So, it is very simple. In case of a huge multi-body system, okay, so doing using Newtonian mechanics is very difficult, and LE becomes very much trivial. So, it is widely used in robotics as well for that reason. Okay. So, now let us use LE approach once again for a one link pendulum or an arm. Okay. So, why I am calling it arm here? Because it is also a 1 degree of freedom robot which may be driven by torque here. Okay. And this is my one link arm, okay, of length L, and theta is the joint angle. So, if it is not provided with any external torque, it can simply swing and it becomes a pendulum. Okay. So, let us say this is your link of mass m hanging over here. So, the rest of the link has 0 mass. This link is of L length, theta is the angle subtended from the vertical at any instant of time. Okay. Mg is the downward force, okay, with which the gravity, Mg is the gravitational force which is acting downward. Okay. So, this is my system, x is along positive x direction and y is along g, okay, gravitational force. Okay, I have taken it like this. You can consider your own frame in your own way, still that would be nice, and you can still deduce the equation of motion for such system. Okay. So, let us start. So, what is my x? X is equal to L sin theta. What is L sin theta? It is basically the distance x. Similarly, y is equal to, y is the lift from the vertical. So, this is my displacement along y, and that is equal to, so this is your L cos theta, and initially it has L, okay, it was here. So, lift is L minus L cos theta. So, lift is y displacement is this. Okay. So, velocity would be equal to x dot and y dot. I take derivative of these two, I obtain this. So, velocity resultant due to the x dot and y dot will be equal to x dot square plus y dot square should give me v square. Okay. So, that gives me v square is equal to L square theta dot square. You see, if you take common L square theta dot square, what you get is cos square theta plus sin square theta, that is equal to 1. So, this is what you can obtain. This you see you can directly obtain also. So, velocity v should be equal to r omega, v is equal to r omega if you remember. So, v here would be equal to L into theta dot. So, v square should be equal to this. You can directly write this also. Okay. So, now the kinetic energy will be equal to K is equal to 1 by 2 mv square. So, I can directly substitute it here and I get this. Again you see kinetic energy is equal to 1 by 2 I into omega square. I is the moment of inertia. For this mass m, moment of inertia I will be equal to, you know, the link is of 0 mass. Okay. So, it is m L square, that is my moment of inertia. Okay. And omega square will be equal to theta dot square, right. So, if I club them together, it becomes 1 by 2 I omega square. So, you can directly obtain it again using various approaches. So, potential energy is equal to mg into this lift. Okay. This is the lift from along y direction. Okay. So, this is your lift. Okay. So, that is what you can put. So, it is mg into L 1 minus cos theta. So, you have now kinetic energy and potential energy in hand. So, what you can do? You can calculate Lagrangian directly here. Let me just vanish for a moment. So, this is it. This is what you can directly obtain. So, it is kinetic energy minus potential energy. Okay. So, this is Lagrangian for the system. Got it? So, now I will use this to obtain my equation of motion. So, using Lagrange-Euler formulation, you can write this time it is joint angular displacement, this is rotary motion, and you will obtain what? You will obtain tau, that is the joint torque. Okay. In earlier case, in a spring mass system, it was linear displacement and force. Over here it is angular displacement and torque. Okay. So, I will again do the bracketed term first, this term, okay, dou L by dou theta dot. Again you see only the first term has got theta dot. So, I will use this and I can obtain this directly. Okay. I will take time derivative of this once again and I will get d by dt of dou L by dou theta dot is equal to ml square theta double dot. Okay. Again the second term, this only has got theta, the first term has got theta dot, it does not have any theta. Again the term which will come out of this is a constant for theta. Okay. There is no theta here. So, it is treated as constant. So, now dou L by dou theta becomes equal to minus mgl sin theta. Got it? So, again you can pack them together to create your equation of motion. In this case, it is ml square theta double dot plus mgl sin theta is equal to tau. Okay. This is the torque. This is the dynamic equation of motion for one link pendulum. Okay. Again, in case there is no external torque, so it should behave like a simple pendulum. Let us see. So, in that case, if tau is equal to 0, so ml square theta double dot is equal to minus of mgl sin theta. Got it? Again, theta double dot is equal to m will go off. So, it is g by L sin theta, okay, minus of g by L sin theta. So, if you remember sin theta for very small displacement, you can take it to theta, sin theta tends to theta for theta nearly equal to 0, and again you can write you see acceleration is proportional to negative of displacement. So, this is equation of motion for any simple harmonic motion. So, and it is equal to minus of omega square x. Omega is your natural frequency of oscillation. So, over here it can again be written as theta double dot is equal to minus of omega n square theta. Got it? So, natural frequency of oscillation, that is omega n, will be equal to square root of g by L, okay, which is a simple harmonic motion without any external torque. So, without any external torque it behaves like a simple pendulum as expected. Okay. Again the same equation of motion can be obtained using our standard approach, that is Newtonian method as well. Okay. But again in this case we find it more easier doing using Lagrange-Euler approach if it is multi-dimensional system. Okay. You have n degree of freedom system like a serial robot. Okay. For those it is very helpful. Okay. So, that is all for this lecture. In the next lecture we will continue using Lagrange-Euler approach to deduce equation of motion of a two-link manipulator using this approach. Okay. That is all. Thanks a lot.